Section 1.7 Parametric Curves. Let's take a look at this figure here. Imagine that a particle moves along the curve C. It is impossible to describe C by an equation of the form y equals f of x because C fails the vertical line test. But the x and y coordinates of the particle are functions of time, so we can write x is equal to f of t and y is equal to g of t. Now, such a pair of equations is often a convenient way of describing a curve and gives rise to the following definition. Now, suppose that x and y are both given as functions of a third variable t, which we call a parameter, by the following equations. X is equal to f of t, y is equal to g of t. And we call them parametric equations. Now, each value of t determines a point xy, which we can plot on a coordinate plane. Now, as t varies, the point also varies and traces out a curve C, which we call a parametric curve. Now, the parameter does not necessarily represent time, and in fact, we could use a letter other than t for the parameter. But in many applications of parametric curves, t does denote time, and therefore we can interpret it as the position of a particle at time t. So our first example, we want to be able to graph a parametric curve. And in this scenario, we want to be able to sketch and identify the curve defined by the parametric equations. The first parametric equation is x is equal to t squared minus 2t. The second one is y is equal to t plus 1. Now, you make a table of values, and the first column we have here is the value of t, and it's ranging from -2 all the way to 4. Now, if we plug those values of t into the first parametric equation, we plug -2 in for the parametric equation for x, and we get 8. If we plug in -1 into that parametric equation, we get the value of 3. 0, -1, and so forth. So you can see what happens when we get the parametric equations for x. Now, again, if we substitute the values of t into the parametric equation for y equals t plus 1, then we get the following results. And then what it basically does is it sets up your ordered pairs. So you have 8, -1, you have 3, 0, you have 0, 1, you have -1, 2, 0, 3, 3, 4, and then 8, and then 5. Okay, so let's see what happens here. Now, we noticed here that at time when t is -2, okay, so at t equals -2, okay, we're plotting the point 8, -1. Okay, then at t is equal to -1, meaning here, okay, the point that we plot on our x and y plane is 3, 0. Okay, and at time t of 0, we're plotting the point 0, 1. Okay, and then if we continue, you can see that we're plotting the next point, which is -1, 2, 0, 3, 3, 4, and then 8, 5. Okay, now basically what's happening here with this curve is that a particle whose position is given by the parametric equations moves along the curve in the direction of the arrows as t increases. So as t increases, and t again gives you an ordered pair, as it increases, it's moving along the curve. Now, if you notice that the consecutive points marked on the curve appear at equal time intervals, but they're not equal distances. Okay? Now, that is because the particle slows down and then it speeds up as t increases. Now, it also appears that in the figure here that the curve traced out by the particle could be or may be a parabola, and this can be confirmed by eliminating the parameter as follows. So let's go ahead and eliminate the parameter. So by eliminating the parameter, we need to look at our second parameter equation, which is y is equal to t plus 1. Now we could look at the first one, but because the second equation allows it for you to be easier to solve for t. So solving for t gives us y minus 1. And what we're going to do is now we're going to substitute that y minus 1 into the second parameter equation for x. So now x is going to equal y minus 1 squared minus 2 times y minus 1. And so then we end up multiplying this out. We get y squared minus 2x plus 1 minus, I'm sorry, not x, y minus 2y plus 2. And then ultimately what we end up getting is this equation, x equals y squared minus 4y plus 3. Okay, so this curve that we have here is actually represented by the function or the equation x is equal to y squared minus 4y plus 3. So what this equation does is in x and y, it describes where the particle has been, but it doesn't tell us when the particle was at a particular point. So the parametric equations have an advantage. They tell us when the particle was at a point, and they also indicate the direction of the motion. Now, no restriction was placed on the parameter t in that example, so we assumed that t could be any real number. But sometimes we have to restrict t to lie in a finite interval. So for instance, using the same parametric equations, we now denote that t would have to be in between 0 and 4 inclusively, and that shows here in the figure. So it is the part of the parabola that we got to see from our previous example. And what it does is it starts at 0, 1. And by starting at 0, 1, meaning that's where you have your restriction at 0, so then this would be considered the initial point. Okay, and then it ends at the point of 8, 5, so this would be the terminal point. Okay, so now again, the arrowhead, okay, indicates the direction in which the curve is traced as t increases from 0 to 4. So in general, there is your parametric equations, x equals f of t, y equals g of t, where t is in between a and b, and it has an initial point and a terminal point depending upon those restrictions a and b. Okay, next, now we want to be able to identify a parametric curve, and we want to know what curve is represented by the following parametric equations. Okay, so in this example, we have two parametric equations. One of them is x is equal to the cosine of t. The second one is the sine of t. And t is in between 0 and 2 pi. Okay, so what we can do is we can first determine what is happening with x and y. Well, we can know that the curve, or it appears to be a circle, and we can confirm this by eliminating t. So how do we do that? Well, what do we know about x and y? Well, we know that we have, if we take x squared and we add y squared, okay, let's substitute the value of x and y from our parametric equations. So if you notice here that the cosine of t is equal to x. So if we take the cosine of t and square it, plus we're going to take the sine of t and square it, then we would end up with cosine squared t plus sine squared t. Okay, now according to our trig identities, what do we know about the cosine squared t plus the sine squared t? Well, we know it's equal to 1. Okay, now we can go ahead and back substitute what we have for cosine squared t plus sine squared t. So we end up with x squared plus y squared, which is equal to 1. So that gives us an equation of a circle. So what that does is it tells us that our vertex, or I'm sorry, the center of the circle is located at 0, 0 with a radius of 1. Okay, so now we're able to then draw, the curve. But what we do know is that t, okay, repeating what we have above, has a restriction, and it goes in between 0 and 2 pi. Okay, so basically what it's saying here is that t starts at 0 and it ends at 2 pi. So this is the initial point, so 0 is the initial point, 2 pi is a terminal point. So on the circle, since we're starting at 0 and we're going to 2 pi, that's the reason why the arrows are going in the clockwise direction. Because again, we're following the pattern of the restriction on this parametric curve. Now let's take a look at another example. Okay, so in this case here, we have a curve that is represented by the given parametric equations. We want to know what that is. And again, we have the same restrictions. It goes from 0 to 2 pi. But now our parametric equations are now, our t is being multiplied by a factor of 2. Okay, so again, let's just use what we did in a previous example. And we know that, again, we have x squared plus y squared. Okay, now let's square the value of what x represents as a parametric equation. And we know that it's sine of 2t squared plus the cosine of 2t squared. Okay, so now when we square the first one, we know it's going to be sine squared 2t. And make sure that you're only squaring the sine, not the value of 2t, plus the cosine squared 2t. Now again, this represents the same identity from the previous example from your trig identities. And this again is going to equal 1. So again, as we said before, we now can then show this and represent this as a circle. Okay, just like the previous example, that has a center at 0, 0 and a radius of 1. Okay, now what is unique about this scenario is that, again, it's still increasing from 0 to 2 pi. Okay, but because the point, okay, we know that the point xy would then equal the sine of 2 times whatever t equals times the cosine of 2 times whatever t equals. Okay, and we know that it starts at 0, 1, okay, but because of this 2, okay, it moves twice around the circle, okay, in a clockwise direction. Okay, so here you're starting at 0, correct? And so here's 0, here's 1, right? Sorry, up here. Okay, and therefore it's now going in a clockwise direction, and it moves twice around the circle because, again, you have the 2. Now, in these two examples, it shows that different sets of parametric equations can represent the same curve. So thus we distinguish between a curve, which is a set of points, and a parametric curve, in which points are located in a particular way. Let's take a look at example number 4. We want to be able to find parametric equations for the circle centered at hk and radius r. So we created our own diagram. We have a center HK and then we have R. So we're going to use these arbitrary variables to find parametric equations for this particular scenario. So what we're going to do is we're going to take the equations of the unit circle and then multiply that expression for x and y by the value of r. So the first step is that we have our parametric equations. X is equal to the cosine of t, and we have y, which is equal to r times, not yet, the sine of t. Okay, now step 2, we're going to multiply, because we have a radius in our particular parametric equations, we're going to multiply each parametric equation by r. So now this is going to become x is equal to r times the cosine of t, and then y is equal to r times the sine of t. Okay, now you can verify that these equations are going to represent a circle with a radius r, and it's centered, the origin traced counterclockwise. Now, the only thing here that it's not centered at 0, 0. It's actually now centered at HK. So what happens with the center of HK? Well, in this scenario here, since it's in quadrant 1 and that's where the circle is located, you're shifting it to the right H units and then shifting it up K units. So if you want to write this in terms of variables, well, the x coordinate would have to either shift left or right with an h. So the h is going to be added to the x parametric equation. Okay, and then the y parametric equation would be manipulated by the y coordinate, which is k, and so k plus r times the sine of t would then represent the parametric equation for y. Because again, for h, okay, you're shifting in the x direction. So that means either the left or the right direction. And then for y, you're going to shift up or down. So that means you're going to shift in the y direction. Okay, let's look at example number 5. Okay, we want to be able to sketch the curve with parametric equations. X is equal to the sine of t and y is equal to sine squared t. Okay, now looking at these two equations, all right, you can see that x is equal to the sine of t, and if you square that, then you get sine squared t. So let's use that observation. So what we can determine here is that if we know that, what did we have to square to get sine squared t? Well, we had to square sine of t to square it, correct? And so therefore we know that x in our given information equals the sine of t. So technically it actually equals y equals x squared. So what you can observe from here is that it's a parabola y equals x squared. So we know that when we want to graph this, we can graph the parabola. Now, there's a couple things that we need to take note here. Now, one of them is the range of the sine function. And so we know that for the sine function, the height goes as far as 1 and goes as low as -1, which means that we know that the sine of x is going to be in between -1 and 1. But again, what do we say that x equals? Well, it equals sine of t. So we can rewrite this that x is in between -1 and 1. So here you have your -1. Here you have your 1. Okay. Now again, remember that the range for the sine function could only go up as high as 1. So now we know that you have a point of this parabola that's going to end at negative 1, 1, and then positive 1, 1. Okay, so what it says here is that if you put points together at the value of t, and that ordered pair would be representative of sine t and then sine squared t. Okay, because you have closed dots at each end, okay, what's happening is that it's going to be moving back and forth infinitely often along the parabola. So as the particle moves from back and forth here, okay, that's the motion of the particle. So we can say that the particle's motion moves back and forth infinitely. And again, according to this particular pattern. All right, let's take a look at the next example. Okay, the next example, okay, it's going to be a simulation. Okay, so we're going to look at an animation of the relationship between motion along a parametric curve, x is equal to f of t and y is equal to g of t, and motion along the graphs of f and g as functions of t. Okay, and we're going to click on the following functions, which is what we just got done using so that we can kind of relate with our previous example. Okay, and now we're going to choose values for A, B, C, and D, and then we're going to animate that, and we're going to see how the graphs relate to the circle. Okay, and then if we choose A to be B and B and C to be 1, and then change D to be 2, well, let's see what happens when we do the animation for that. So I'm going to go ahead and click on the animation here. Okay, and so I'm going to go ahead and take a look at our parametric curves animation. Okay, and so again, what this module does is it graphs parametric curves from several different families involving trigonometric and polynomial functions. Now, in addition to the parametric curves themselves, the graphs of x and y as individual functions of t are shown. Now, you can observe the behavior of the values of x and y as t increases, and then watch how the parametric curve given by x equals f of t and y equals g of t is formed with these values that are working in tandem. So let's take a look at the instructions here. Okay, so up here we choose our available families of parametric curves. So since we want to compare it to the previous example, we're going to pick that first one. Okay, and then what you're going to do is we're going to drag the slider handles and then click on a slider bar or click on a number above a slider to adjust the coefficients in the equations and then update all three graphs. Okay, now the parametric curve is shown in the upper left-hand diagram. So here is where the parametric curve is. Okay, and to the right over here is the graph of y as a function of t, and over here this is the graph of x as a function of t, I believe. Yes. Okay, and you're going to rotate to align the x-axis along the x-axis with the x-axis on the parametric graph. Okay, and then what we're going to do is we're going to drag the t slider located below the function graph of t to change the value of t. So let's take a look at this information. So in that example that we saw, they wanted us to make sure that in these equations that A is going to represent 1. Okay, we said that B was going to represent 1. And then we said that, that's C, and that's B is 1. and then we said that D was also going to be 1 for the first example. Okay, now we can either go to 4 pi or we can go to 2 pi. So let's see what happens when we restrict T to go from 0 to 2 pi and select animate. Okay, so again, you can see what's happening with each particular situation. So if I slowly start at 0, okay, look at where your point is. It starts at 0 here on the y function of t. This graph is starting here, okay, and then over here it's starting here. This is your parametric curve. So as I move along, you can see that each particular graph is showing the particle's movement. Now, if we decide to change the value of D to 2, let's go ahead and run that animation. So again, you can see that the curves being drawn change as the values of T increases. Okay, so for example number 6, okay, we want to be able to graph x as a function of y. And sometimes it may be better to graph these equations, these parametric equations, using a graphing device. So in this example here, we're using a graphing device to graph the curve x is equal to y to the fourth minus 3y squared. So we only have one equation here, okay, and we need to have two parametric equations, okay, and they're not in terms of t. So if we want to write this function in terms of t, then we need to set something equal to t. So what we can do is we can let y equal t, okay, and then substitute it into the parametric equation for x. So we'll call that first equation a. And so now x is going to equal, instead of y to the fourth, now it's going to be t to the fourth minus 3t squared. So that represents the parametric equation for x. But we also need a parametric equation for y. But since we stated that y would equal t, then there is our second parametric equation. So using these parametric equations to graph the curve, we can obtain the graph from figure 9. Okay, and it would be possible to solve the given equation for y as 4 functions of x and then graph them individually, but the parametric equations provide a much easier method. So let's go back here. So in general, okay, if we're given a function, so this is a general rule. So if we have the following scenario above, and if you're given a function in terms of x as a function of t, okay, then what you would do is you would let y equal t and substitute it back into the equation. And then in turn, what happens here is that you would then rewrite it in terms of x, which is equal to whatever that is according to t, and then y is then going to become the function of t. Now, graphing devices are particularly useful when sketching complicated curves. Now, for instance, curves shown in this next slide would be virtually impossible to produce by hand. Now, one of the most important uses of parametric curves is in computer-aided instruction, which is called CAD. And in the laboratory project that you see later on in Chapter 3, you investigate special parametric curves called Bezier curves that are used extensively in manufacturing, especially in automotive industry. And these curves are also employed in specifying the shapes of letters and other symbols in laser printers. Okay, now our next example, okay, talks about a cycloid. Okay, so what I'm going to do is I'm going to go ahead and open up that tutorial first before we get to this question. Okay, and we're going to go over the family of cycloids. Now there's three families of cycloids, okay, but we're going to go ahead and look at the first one, which is the cycloid. All right, so now a cycloid, what it describes is the path of a fixed point on a circle as the circle rolls along a straight line. So here's your circle and it rolls along a straight line. Now this module allows you to watch the curve being formed by rolling a circle of different radii. So we can change the radius and to see what it looks like. Now you can then view curves formed by a fixed point on a circle rolling along another circle, either on the inside, which is called hypocycloids, which is the second family of it, and then you have epicycloids on the outside of the circle. Okay, now by varying the radii of the two circles, you can investigate a wide variety of beautiful patterns. Now let's take a look at the instructions. Okay, we're going to select cycloid. Okay, and then with that cycloid, we're going to follow the path of a fixed point on a circle rolling along the straight line. Okay, and it's given by the parametric equations, where the parameter now, in this case, because we're dealing with a circle, is theta and not t. And the radius is the radius of the circle, and again, the parameter is theta. And what we're going to do is we're going to drag the R slider, okay, to change the radius of the circle. So this is going to change the radius of the circle. And then we'll click Animate button to start the circle rolling and observe the path formed by the fixed point on the circle. Now, we can also use the theta slider here to then show it in a slow process. So as it goes from 0 to pi, you see what's happening there. Then it goes to 2 pi, and it touches the x-axis. Okay, then it goes to 3 pi, and it's at its peak, and then back down to 4 pi again on the x-axis. And then back up to 5 pi at its peak, and then 6 pi on the x-axis. So this tells you whether it is increasing or decreasing. So where is it increasing? Well, we can see that it's what? It's increasing from 0 to pi. But then it's decreasing from pi to what? 2 pi. Increasing from 2 pi to 3 pi. Decreasing from 3 pi to 4 pi, and so on. So again, these animations allow you to see this a little bit better. Okay, now let's go ahead and hit Animate so you can see what happens when we just go ahead and watch that. Okay, so again, we can change the maximum amount of revolution there. So if we wanted to go to 4 pi, then it's going to stop a little sooner. Okay, so let's go ahead and click Animate. So it's going to go there. Okay, now taking a look at our example. Okay, now that you've seen that, okay, the curve traced out by a point P on a circumference of a circle rolls along a straight line is called a cycloid. And if the circle has radius r and rolls along the x-axis, and if one position of P is the origin, find the parametric equations for the cycloid. Okay, so if you notice, now we choose a parameter, the angle of rotation being theta of the circle. Okay, so that's when theta is equal to 0, when P is at the origin. Okay, so very important here. So where it starts at the origin, theta, the angle is 0. Okay, when the point P is at the origin. So there's no angle at that particular scenario. Okay, now suppose a circle has rotated through theta radians, because the circle has been in contact with the line, as we can see when it rolls, and that the distance it has rolled from the origin is the following. Okay, so it's going from here to here, right? Okay, now this is actually the distance that we're looking at. Okay, so the circle, as it's moving, right, and this is the green part of it. Okay, the circle is moving, and that's the distance. So this is the arc of PT. So we can say that the distance that it's traveled, now remember, distance has to be positive, so we're trying to find the distance from here to here, which is OT. So the distance, which is the absolute value of OT, okay, is going to equal, okay, well, it's going to equal this arc. And that arc goes from P to T. So this is arc PT, okay, which equals R times theta, because that is the definition of the arc. So therefore, we can say that the center of the circle is located at the following. So the center of the circle is R times theta R. Now let's consider the coordinates of P to be X and Y. Okay, so we're saying here that this point here for P, since they're arbitrary points, are going to be X and Y. Okay, so let's go ahead and do that. So in part 3, we're going to let the point P represent the arbitrary points X, Y. Okay, so now let's take a look at the parametric equations. So again, we're going to have a parametric equation for X and a parametric equation for Y. So again, X is going to equal the distance from O to T, okay, because that is the X distance. So that is the absolute value of OT. Okay, and then what it's going to then do is that in order to find this distance, you got to subtract PQ. So here, you're subtracting PQ. So you're subtracting the distance of PQ. Okay, so if you notice down at the bottom here, okay, the distance from O to T, which is what was given now from the arc equation, is R times theta minus, okay, well, what is PQ? Well, that represents a right triangle. And if you recall from a right triangle, that distance is representative of R times the sine of theta. So now you're going to subtract R times the sine of theta. Okay, and so now we can say that X represents if we factor out the R, theta minus the sine of theta. Okay, so now let's take a look at the Y. Okay, now in order to solve for Y, okay, now we're going to use TC. So here is the distance from T to C. Okay, and then we're going to subtract QC. Okay, so that is this distance. Okay, now again, because it forms a right triangle, we know that that distance is going to represent R times the cosine of theta. Okay, and the entire distance of TC is R. So Y is going to equal R minus R times the cosine of theta. So ultimately, our parametric equation for Y is then R times R times 1 minus the cosine of theta. Okay, so that basically proved a theorem. And not necessarily a theorem, it's parametric equations of a cycloid. So the parametric equations for a cycloid are the following. We have x, which is equal to r times theta minus the sine of theta, and y, which is equal to r times 1 minus the cosine of theta. And that means that theta would have to be any real number. Okay, now one of the cycloid comes from one rotation of the circle. So it is described by the restriction 0 to 2 pi. Although in equations 1 were derived from figure 14, which illustrates the case where theta is in between 0 and pi over 2. Okay, so again, we want to make sure that we're careful of our restrictions. Okay, last, although it is possible to eliminate the parameter theta from equations 1, the resulting Cartesian equation in x and y is very complicated and is not as convenient to work with as parametric equations. So here, looking at figure 15 and figure 16, you can see that you have a cycloid. Now, one of the first people to study the cycloid was Galileo, who proposed that bridges be built in the shape of cycloids, and who tried to find the area under one arch of a cycloid. And so later, this curve arose in connection with the brachistochrone problem. We want to find the curve along which a particle will slide in the shortest time under the influence of gravity from a point A to a lower point B, not directly beneath A. And the Swiss mathematician John Bernoulli, who posed this problem in 1696, showed that among all possible curves that join A and B, as in figure 15, the particle will take the least time sliding from A to B if the curve is part of an inverted arch of a cycloid. Now, the Dutch physicist Huygens had already shown that a cycloid is also the solution to the Tato-Crone problem. That is, no matter where a particle P is placed on an inverted cycloid, it takes the same time to slide to the bottom. So Huygens proposed that a pendulum clocks, right, which he invented, should swing in a cycloidal arcs, because then the pendulum would take the same time to make a complete oscillation, whether it swings through a wide or a small arc.